Now we're proving this wonderful theorem today. This is the deal. What is our goal today? Theorem. What does the theorem says? CP star is always at the primitive root, right? That's where we're headed. Okay. And these are the tools that you might quickly agree, oh, that makes sense. Right? This is our goal. What does the first lemma says? If x is an element of Zn star, not necessarily prime, and if the order is s times t, order of x to the s is t, right? Okay, let's prove it. Is that exercise 5? Is that correct? Okay, exercise 5. Prove this lemma. How do you prove it? What formula comes to your mind? That's it, one that we memorized yesterday, last time. Yes, exactly. Order of x is given. It is about x to the something, right? Yeah. All right. Make sense? Question? Right, we're going to prove the next lemma together. These tools are used to show the existence of a primitive root. So let's begin the proof of lemma together, and at some point I might turn it into exercise or not, just asking questions. I have two elements in this, z mod n star. One has order s, the other one has order t. The condition is that this s and t are relatively prime to each other. Fair enough? Then we want to show x times y in that multiplicative setting has order s times t. Right? Might write down the statement and understand what's involved in there. All right. So this is our goal. There are the condition. There are two things you have to show. Order is something. This is nice calculation, right? But it's not directly applicable in here because of x times y. So what we're going to do is that we're going to compute x to the xy raised to st. Fair enough. Why we're doing this? What is our expectation? This is going to give you 1, right? Because we're in the class and it's not congruent to 1. It's 1 in here. Because of the commutativity, you know this is true, right? What is x to the s? X to the s? Why is that 1? Order of x is s, so it's 1. How about y to the t? Order of y is t, right? So it's 1, 1 equals 1. So I raised x times y to st power, you got 1 back, right? You're right. Yeah, I was daydreaming. st, thank you. st, so that should be organized into xs, t there, and yt, s out there. That's like that. Thank you so much. This is 1 times 1 raised to the tth power, and that's 1 raised to the nth power. So that's why it's 1. Okay, thank you. What is the next thing we should do is that this is really order, right? Order is not something divided. I think I approach it like this. Try, well, if, suppose xy raised to the nth power is 1, right? And we have to show that this L is greater than s equal t, or divisible by st, something like that. Then it's a truly the order. Okay? This is the smallest. That's what we have to show. Isn't that right? Okay. Let's proceed. What do we know about this is the x to the L, y to the L equals 1. Is that right? And I separate it like this. X to the L equals y to the negative L. Fair enough? Then I apply order formula to there. Order of this one is equal to order of that one, obviously, because the same elements, right? Fair enough? So let me make that one as an exercise. What conclusion do you draw out of this thing, right? So here's exercise number 6. What's your conclusion from the following statement? Order of the order of x to the L equal to order of y to the negative L, right? In particular, it follows is exactly the same element. So if you look at the order, we have a formula to apply, right? What formula am I talking about? The same formula we used in here. So if you enter these formula and compare to each other, and using that, so far we haven't used the SNT relatively prime. Okay, enter the order formula, use this ST relatively prime, and see which conclusion you can get out of it. Bless you. All right, how about this formulation in here? That's okay, right? Order of this one left-hand side is S divided by GCD. Order right-hand side is S divided by negative L, but that's GCD being positive, so you can change the positive it's there. So what conclusion did you draw in here? Using that S and T are relatively prime. This is a divisor of S, right? S divided by something, right? And T divided by something. And they're equal to each other. If they have no relatively prime, I mean, they have no common factor. What conclusion do you draw about the GCD of S and L? No, if it is 1, then it's going to be whole S, right? Where it, it is L, SX. The whole thing should be there, right? Yeah. It should be gone. 1 is the only thing that can equal the right hand side, right? And GCD of T and L, that should be T. That's the conclusion. Knowing that S and T have no common factors. All the factors should be in there. So that should be the entire S. Oh, that makes sense? Continue, since this is a better situation. See what you can say about L. It's all about L. We started with this condition. Anything that raised to L power is 1. So what kind of condition would we have about this L? Right, this right here, L is divisible by S, right? If the GCD is S, S must divide L as well, right? And T divide L as well. That's the very definition of GCD is common factor. All right, what's the conclusion here? What divides L? S times T. And what is the important condition we're using right here again? Because, no, if S divides L, T divides L, S times T divides L, what's the counterexample? It is not in general true. GCD of S and T is equal to 1. That was the key here. GCD of S and T equals 1 allows you to product this divides L, right? So what ultimate conclusion do you want to draw here about L so that we can conclude that S times T is truly the order? What is greater than what? ST is less than L. No matter what you raise, you get 1, ST is smaller, guaranteed, right? Therefore, ST is the order. So here you write, all right, X times Y has order S times T. Fair conclusion? So that's the answer to exercise 6, but we actually proved that from there, the order of this one is S times T. Fair enough? Okay. Now, if you're looking at an order of elements with order S, elements of order T, if they're relatively prime to each other, if they multiply each other, the order multiplies as well. That's the conclusion we have. That's that statement. All right, here's your ultimate challenge today. What is the exercise number? 7. Use those two things that you learned and answer this question. P is 1021, prime number. And P minus 1, why P minus 1? Why am I looking at P minus 1? Right, phi of P. That factors like this. 2 to the squared and 3 and 5. And what is our goal? We're looking for a primitive root generator of a cyclic group, right? They said it's going to work, so we're looking for it. So I looked at the order of P. What is it? 2 squared and 5 and 17. Compare that with the full order we want to reach, right? Is that good enough? Not good enough. How about 3? I tried it. Mathematica gives me 2 and times is 17. Is that good enough? No, it's not. I looked at 5. 5 didn't reach it, right? But you can play with the 3 and 2 and 3 and 5 to reach the full order. Using what? Two lemmas? Not Chinese remainder theorem. The two lemma we just learned, right? Two lemma we just learned, right? Think about here, lemma, you can create an order like S times T, but you have to make sure they're relatively prime to each other, right? Order of that element. If you look at this order, they're highly not relatively prime to each other, right? So you have to pull out two elements that are relatively prime to each other. It's orders multiplied, you get that out of it. That's your challenge. Exercise 7. Do you get it? He seems excited. So let's hear him. What is your G? Staring at him. Are we going to stone him or are we going to praise him? Which one is it going to be? Is it working? That's right. Very good. Right. Let's look at examine this one. What is the order of not the MRD? What is the order of 5, 5, 17? Can somebody tell me? Not Andrew. What is the order of a 5 versus the 5 to 7? We could hear 3, right? If you put that on the top here, you're left with whatever the rest of the part, right? Now you look at order of 2. What's the order of 2? Is it 2 to the second and 5 and 17, right? Are they relatively prime or not? They are relatively prime. Therefore, if you multiply these two, order multiplies, right? So the order of, yeah, you got that. It's the old Putnam seminar skill. And he put it out. No, just kidding. All right, that's the order from that group. Yay, we found what? Primitive root. Thank you. That was our goal. Yeah. All right. I'm not going to disappoint you. I have one more for you. So you can do on your own. All right. Try it again. That's 8. You have one, Keely? So why don't you go for it? G equals 97. 3 here is a 5. That's all we need. So it checks. Whatever it is. Well, that's not the only one, right? Yeah. Okay. Make sense? So we took care of 2 of the primes in the whole number of primes out there. So let's do the general case. Question? That's worked out. All right. Here's a key thing. We're heading toward to that proof. We had all the keys right there. You just have to understand this field property. All right. Let's prove that there is primitive root mod for all primes p, right? Easiest prime p, what is it? 2. So we're not going to bother to write something else. All right, let's look at it. Lemma. Let's look at lemma here. This lemma has a name actually. Anybody remember the name? One of those, right? I think it was Lagrange, was it not? It was Lagrange. At most, you know, yeah, yeah. It's just too big a gun to handle that. Yeah, yeah, yeah. It's a polynomial. Because the field, you can keep dividing it. If you have a solution, degree knocked down by 1, you can't go past m. Things like that. All right. So if you're looking at m that is less than equal to p minus 1, um, this only has at most m solution, right? That makes sense. Good. So the proof of this theorem goes like this. Proof. Let A be an element in GP star, which is FP star now, with the largest order, right? And we want this thing to be P minus 1, right? Largest order you can have inside FP star is P minus 1. So what do? We suppose what? Yeah, the order of this one is, let's say, n, and is less than p minus 1, right? Fair enough. The next claim, I'm going to give you the chance to explain it. That's our exercise number what? 9, right? Exercise 9 is that prove that there is B in FP star such that its order, we're going to call M, right? Let's not call M. Let's call L. Does not divide N. It's pretty hard, actually. All right. There is an element B out there. It's less than P minus 1. There's an element B. Its order does not divide N. Here's a hint. It's too hard. Consider the equation x to the n equals 1 in FP star. And count the number of solutions. That might help. Well, let's read it together again. All right, we suppose that order of A, which is n, is less than p minus 1. And I'm claiming there is a B element out there such that its order does not divide n. And hint I'm giving you is consider this equation x to the n equals 1 in FP star and see if you can count the number of solutions. How many solutions are number there? How can you answer something like that? Nothing's given, but n here, where does the n come from? Order of A, right? Let's answer it together. Do you know how many solutions are there x to the n equals 1? How many solutions? 1? At least 1. There are more. 1 is a solution, yes, but there are more. Obvious one in there. A. Isn't that right? A is a solution. A to the n equals 1. So we found 2. So who wants to go next one? 1A. A power? Like that? A second? How about A is the second? Can somebody prove that A is a solution? All you have to check is that this is 1, right? Is that right? Yes? Third power? Fourth power? So how many? At least n, right? We found n works, right? But why is it exactly n? No. Why is it exactly n? So all these things we have distinct elements, right? These are all distinct, isn't that right? Why is it distinct? Because it's the order of n. It's all distinct. There's all solution in here, right? So we found n of them. But why is it precisely n? Were there no more out there? No, that's this one. This is counted. Of course there's n of them, right? But what if it's elsewhere out there and deep in the corner of FP star we haven't touched? There it happened to satisfy this one. Why can't that not happen? Nope. What is that? I think right. How about this guy? Right, what's M here? We're looking at. At most how many? n solution, right? But we found n solution. Therefore, that's it. Why that happen? Because FP is a field. That's the key. All that we use here is that at most M solution uses FP as a field. If you look at other things, the Z mod n where n is not prime, is not a field, this fails, so this argument fails. All right. So still we haven't answered that. We just counted that this is exactly n solutions there, right? We just dealt with that hint. Consider the equation x to the n equals 1. It has precisely n solutions, right? What about that b? If b has order L, and if L divides n, let me give you this much. What is the b to the n? Not 1. Let me see. If L divides n, then b to the n is 1. Isn't that right? Because order of L, right? Order of b is L, so b to the L is 1, so you can go up to that, right? Does that mean b is inside? B is inside this a to the first all the way up to the a to the n. Isn't that right? This is a collection of everything that raised to the n power becomes 1. So if the order of b divides n, it must satisfy this equation. Therefore, b must be in there. Isn't that right? Yeah. So we assume that it is not b minus 1. Therefore, there must be an element outside this one in here, right? Is that correct? So here is the final bit. Choose b that is not inside this one, right? Is that correct? Then what conclusion do we have? The order of b, L, must not, what is the rest of the clause? Divide n. Can you explain that again? If it divides, it must be in there, right? It's contrapositive statement. If it is not in there, it's out there. So why can't we choose that b is outside element? Because this is not p minus 1. There must be something out there. This is less than p minus 1. So if I choose b outside this thing, I guarantee that order of L does not divide n. Is that right? Okay, so that's the answer to exercise 9. Okay, give yourself 2 points. That was too hard. That was too hard. All right. So if order of L does not divide, and you can we write it like this? Order of n here. That was n, right? That was n. So I'm going to use prime q, e here, n1, b prime q, f there, and this was L1. So I'd like to claim that there must be prime q such that you can write a as a prime power and rest of the part, the full prime power, and n1 GCD of n1 and q is 1, and GCD of L1 and q is 1. And most importantly, because b does not divide a, the power of f must be greater than e. I want you to understand this last bit. Can someone explain why that has to be true? F is greater than e? It has to do with that statement. Right. If it does not divide, there must be some prime factor in here. It must be a higher power. If every prime factor involved is a lower power, that means the b order of b divides order of a, right? Isn't that right? Because of that, there must be at least one prime such that its power is greater, so that it order of B does not divide that. Fair enough? All right. Final exercises today. Exercise 10. Find an element of order q to the f times n1. Why am I looking at q to the f times n1? Here is a q to the e times n1, right? That's right. It's a bigger. That's right. This would be bigger order than that one, right? Because it's bumped up the power. Isn't that right? So will that violate our assumption on A? What is our assumption on A? It has largest order, right? If I can find an element with order q to the f times n1, isn't that a bigger number than this one? So I found an element of order bigger, right? Therefore, contradict everything. That wasn't the order less than b minus 1. So what is the answer to this one? That's your 1-minute exercise. We practiced it before, and you guys were happy about it. You're looking at this one and that one, right? Which one has order q to the f times n1? Right. So a to the what power? Q to the e, thank you. B times b to the L1, that's right. This one has order q to the f and 1, right? So we're supposed to observe that this is greater than what number? Q to the e times n1, which is the order of a, right? So why is that a problem? Right. A is supposed to have the largest order, right? But I have even larger order. So let me scroll back and you stop and point me. Oh, now because it's a contradiction, that must be incorrect. So the proof started there. Where should I go back and fix that? Okay, I found a contradiction, so this must be the other case. Where is it? P minus 1. Because of that, we pull out B outside that set of A1 through then, right? And then we're able to cook up A times B and then large order, right? So it contradicts the largest order. Therefore, this guy must be P minus 1. That is a proof of what? Proof of it has primitive roots. Yeah. You don't have B that is outside. That's why. Yeah. If it is equal to P, then here B here is outside the set here. It doesn't exist because 1 through P minus 1 is everything. Everything. That's why. Very good.